Okay, these are some homework problems from Chapter 6. This is actually just Unit 4 homework in general. So we'll start with 65 off Chapter 6. It says friction provides the force needed for a car to travel on a flat circular track. Okay, what is the maximum speed at which the car can safely travel if the radius of the track is 80 meters? And the coefficient of, actually we'll say static friction here, is 0.4. Because the car won't be slipping on the road at all. The tires will be rolling, but there won't be any skidding, hopefully. So the first thing we want to do is set up a free body diagram. We know there's only one force acting on it to accelerate it towards the center, and that's the centripetal acceleration force, which we know is friction. Okay? And that equals mass times the centripetal acceleration then, because that's the only force causing it to stay on the track and not slide off. Take friction away, and there's no way to go around in a circle on ice, right? You'll just start sliding straight. Okay? If there's no friction at all, you cannot go in a circle. So we need to do this. This is the frictional force, which is just mu sub s. Mu sub s times the normal force. And then the centripetal acceleration on your formula sheet is v squared over r. The normal force is mass times gravity. And the masses will cancel. And so you have mu sub s times g equals v squared over r. We're solving for v. We have mu sub s is 0.4, and we have the radius is 80. So 0.4 times 9.8 equals v squared over 80. Multiply both sides by 80, and take the square root of that. And you get the velocity that you can travel around a circle is about 17.7 meters per second. If you go any faster than that, then what's going to happen is the force centripetal acceleration will be greater than the frictional force, which is a problem. The force required to accelerate you towards the center of the circle and keep you on that circular path would be greater than the force of friction that can provide you that force. So then you'd slide off the track, or you'd go straight because of inertia. So the answer is 17.7. All right, next problem off Chapter 6 is 66. It says a carnival clown rides a motorcycle down a ramp and around a vertical loop. The loop has a radius of 18 meters, so that's supposed to be a circle. I realize it's not the greatest, but imagine that that's a circle. And we know it has a radius of 18 meters. What's the slowest speed the rider can have at the top of the loop to avoid falling? So we're going to do a free body diagram at the top of the loop. We have gravity pulling down at that point. The hint is that at the slowest speed, the track exerts no force on the motorcycle. So this is the only force acting on it then. There's no normal force from the track itself. So what that means is that this mg has to be equal to the force of centripetal acceleration, which is the mass times centripetal acceleration, right? Because that's the only force causing this acceleration towards the center, is the weight at this point. That's the force that's responsible for the motion of the circle at this point. Okay, the masses are going to cancel. So you have gravity equals centripetal acceleration, which is v squared over r. Multiply both sides by r, and take the square root of both sides, so you get your answer, which is the square root of the radius times gravity. Radius is 18, gravity is 9.8, and your final answer should be 13.3 meters per second. Okay, let's do 62 as well. I'll go back and do that one from Chapter 6. It says an athlete whirls a 7-kilogram hammer 1.8 meters from the axis of rotation, so that's the radius, 1.8 meters. It says if the hammer makes one revolution in 1 second, they just gave us the period. The one revolution is the time it takes for something to do one revolution is the period. And it wants to know what the centripetal acceleration of the hammer is, and therefore what is the tension in the hammer. Centripetal acceleration is on your formula sheet. There's two different formulas. There's v squared over r, and there's also this other formula that's on there, which is right here, 4 pi squared r over t squared. So we might as well use that formula because we're given the radius, we're given the period. So this one will make more sense for us to use. 4 pi squared, the radius is 1.8 divided by 1 second squared, which is just 1. That gives us centripetal acceleration of approximately 71, and it's an acceleration, so it's meters per second squared. Okay. That's the first part to the question. The next part is what's the tension? Well, F equals ma can give us the tension because there's only one force acting to cause this circular motion, and that one force is the force of tension. So this is the correct formula. The force of tension equals the mass times the centripetal acceleration. They gave us the mass of this thing was 7 kilograms, and the centripetal acceleration we found was about 71. So that gives us a force of tension of 492.4 approximately, if you keep this in your calculator. And that's newtons. 497.4. 67 is the last one for chapter 6. It says a 75 kilogram pilot, so we have a pilot with 75 kilograms, flies in a loop as shown. At the top of the loop, when the plane is completely upside down for an instant, the pilot hangs freely in the seat and does not push against the seat belt. So what that means is that there is no normal force, basically, from the air molecules, from the lift on the plane. Therefore, there's no normal force attributing to the acceleration. He's basically in free fall at that point. And the free fall would be mg. That's causing him to accelerate towards the center of the circle. Okay. The airspeed indicator reads 120 meters per second. And the question is this time, what's the radius? So exactly like the clown going around the hoop in the other problem, but this time we're trying to find the radius instead of the speed. But exactly the same problem if you draw a free body diagram, which I kind of have here. There's only one force, and that's mg. So the force of centripetal acceleration equals mass times centripetal acceleration, F equals ma. In this case, that force is mg. The masses cancel, so you have gravity equals v squared over r again. Only this time you're solving for the r. So gravity's 9.8. The velocity was 120 meters per second. So we need to square that. Divide by the radius. So this time you're solving for r. So I would multiply both sides by r and divide by 9.8. So you have 120 squared over 9.8 is your answer, which gives you 1,469.4. And that's the radius, so that's in meters. All right, so 52 is now from chapter 7. It says that Jupiter is 5.2 times further from the sun than Earth is. Find Jupiter's orbital period in Earth years. There's different ways to do this. You have a formula for period in your formula sheet, which is 2 pi times the square root of r cubed over g times the mass of the sun. This way will work. You can actually get the value for the mass of the sun on page 173 of your book, and you can get the average orbital radius from Jupiter to the sun on that same table. So you could use this if you wanted to, but based on the information they gave us, they kind of want us to use Kepler's third law. They want us to use this. So we're going to do the period. We'll say A is the Earth. And it doesn't matter, by the way, these are interchangeable. You could reciprocate both sides of this fraction. It doesn't matter, but we'll say B is Jupiter. All right, so then the period that, the time it takes for Earth to get around the sun, we know is 365 days. So I'm going to write that down for the period of A. And I'm going to convert that to seconds real quick. So we know that one day has 24 hours. Oops. And we know 1 hour is made of 60 minutes. Or how about I just do 3,600 seconds? All right, so the hours will cancel, the days will cancel, and I get the period of the Earth in seconds is... actually, we don't have to convert this to seconds. We can use whatever unit of time we want, because whatever unit of time we use there is what we're going to get out of the bottom. So you can do this if you want, put it in seconds, then what you're going to get out is seconds for the period for Jupiter around the sun. We might as well just use whatever we want. So let's use the simplest thing we can, which is 1 year. And that's what it wants it in anyway. Thank you. So this will be 1 year divided by what we're trying to find, which is the period of Jupiter around the sun. And that equals the average orbital distance from the Earth to the sun, which we'll say is 1. And then that way we can use 5.2 for the average orbital radius of Jupiter around the sun. So that's really all we had to do. I made it way harder than I had to. And we can just solve for TCB. So I would raise both sides to the 1/2 power to get rid of that power. And then you have this. And then I'd probably just solve for this and do the reciprocal. So TCB equals 1 over this value. 1 over 5.2 to the 3 halves. So that's something we can do on our calculator pretty easily, and it gives us, all right, we got approximately 11.9 years, or approximately 12 years then, in Earth time for Jupiter to get around the Sun. Okay, next question is 63 off chapter 7. It says if small planet D were located 8 times as far from the Sun as the Earth is, how many years would it take for the planet to orbit the Sun? Let's try using the same formula. Let's try using Kepler's third law. And this is off your formula sheet. So we'll call planet A the Earth. And some small planet, planet D, we'll call B on our formula. Okay, so the period that it takes the Earth, we'll say 1 year again. So we're trying to find out how many years it would take this planet to orbit the Sun. Okay, and the distance that the Earth is away, we'll call 1, in which case this planet's 8 times as far, so we can call that 8. And then all we need to do is solve for the time it takes for this planet to get around the Sun. So once again, if we raise that to the 1/2 power, we can get rid of that exponent, or take the square root of both sides, essentially, which is the same thing. And then, so that means the time it takes for it to get around. So then this would be, if you reciprocate this side and this side, you'd have this. So this is what you need to type in your calculator, and if you do that, you should get about 22.6 years then. All right, gives us the moon is 3.9 times 10 to the 5th kilometers from the Earth's center. So I'll just do 10 to the 8th meters. And then it says, and 1.5, oh, gotcha, from the Sun's center. So distance that the moon is away from the Earth, and the distance that the moon is away from the Sun is 1.5 times 10 to the 8th, which I'm going to have to add 3 decimal places to that because we're talking about kilometers. I'm going to be in meters, so I'm going to do 11. If the masses of the moon, Earth, and the Sun are given, find the ratio of the gravitational forces exerted by the Earth and the Sun on the moon. Okay, so this is just a lot of plugging into this formula. The formula is universal gravity. So we're going to do, for the first one, we'll do the Earth and this. So we'll do Earth and Moon, which we need to use the distance between them as well. So that gives us 6.67 times 10 to the negative 11 times the mass of the Earth, which is 6 times 10 to the 24 kilograms, times the mass of the Moon, which is 7 times 7.3 times 10 to the 22 kilograms, all divided by the distance, which I need to be in meters, so I got the right distance for between the moon and the Earth, which is 3.9 times 10 to the 8, and I do need to square that. So you're going to have to type all this into your calculator, and you should get 1.9 times 10 to the 20 newtons. Okay, now we're going to do the same thing, only this time we're going to do it with the numbers for the Sun. So we're going to use the same formula, so it's G, which is 6.67 times 10 to the negative 11, times the mass of the Sun, which is 2 times 10 to the 30, times the mass of the Moon, which is 7.3 times 10 to the 22, divided by the distance between them squared, which is 1.5 times 10 to the 11 squared. Now if you simplify that, you should get 4.3 times 10 to the 20. Now if you just do a ratio, 1.9 times 10 to the 20 over 4.3 times 10 to the 20, you get the ratio of the forces. So this is like 1.9 to 4.3, or if you flip it, you can write it as, the other way around, 4.3 to 1.9, which gives you a decimal of 2.26. So basically the Earth pulls on the moon a little over twice as much as the Sun pulls on the moon.